Hello everyone. So welcome back to my YouTube channel. So today I'm going to explain what is AVL tree and how node deletion is working on AVL tree. So don't worry, I'm pretty sure most of you guys never seen AVL or don't know what is AVL like I did before. And I will explain everything step by step. So those who don't know what AVL is will know what is AVL tree at the end of this video. So first of all, AVL is simply a method using binary search tree, but more complicated and much easier for data structures. It means every time we insert or delete in node, the tree balances itself automatically. But binary search tree doesn't do that. So first, let's talk about what is AVL tree more detailed. So AVL tree was built by two engineers named as Adlerson and Landis, who take their first letter of their names and AVL tree. So before that, let's talk about what is BST or binary search trees mean. So binary search tree is simply has simple property, which is left child is less than parent child and right child is always greater than parent child. What does this mean? So as you can see here in record, 5 and 4 are two nodes in same linear method, and 5 is a parent class and 4 is less than 5. So it's always sorted, and 4 is parent class of 2, which means 2 is child class. So but this, as you can see, this is not actually balanced, so that they make AVL tree to not, so because of the not balance, to solve this problem, the AVL was created by the scientists I mentioned earlier, with two main rules, such as the height difference between the left and right subtree of any node must be -1, 0 or +1. What does that mean? So as you can see here, balance factor should be equal to height of left subtree divided by the right subtree. I'm pretty sure you don't get it by just saying it, so I will demonstrate it. So here we have a simple tree. In here, if we take both sides, they have 3 by 3 nodes. So if we subtract by left side with right side, it will become 0. So this balance factor is, according to balance factor, this has 0. So as I mentioned, balance factor should be 0, 1 or -1. With previous occasion, this rule was satisfied. So therefore that tree was balanced. Let's take some another example. In the same tree, if we take this part of nodes, there are 2 nodes and 1 node. So if we subtract it and get the balance factor, you can see there's only one balance factor, which means, and also it becomes more and more balanced. So what happens if this not in the range of 0, -1 or +1? So what happens if the balance factor is not 0, 1 or -1? In this occasion, this means that tree is not balanced. So we have to do rotation. So there are 4 types of rotation in total, which will be LL or LL, RR, LR and RL, which means left rotation, right rotation, left right rotation and left right left rotation. So from now on we will talk about that. So first let's talk about right rotation, which will happen when the left side of subtree is too heavy, and we will have to do the right rotation so it will be balanced. Like in this case, we have a simple array 10, 20, 30, 40 and 50 and 25. It will become array like this, but it's not actually balanced. So what we do is do a right rotation to this and make it balanced. Like this same way, and to the other side left rotation will be happen. This is the opposite of what is happening in right rotation. If happen when we insert a node in the right subtree of the child is heavier, so we tree leans to the much to the right. For example, in we insert 10, 20 and 30. Now the right side is too heavy. We fix it by performing a left rotation. Next will happen is left-right rotation, which will happen if the imbalancing zigzag way. We use double rotation or LRO, RL method to make it fix. So again, like this is not balanced, so we will make it something like this. And so this is another method of we use to double rotation, which is RL. And yeah. So next, let's talk about node deletion. So what happens in node deletion is actually there's two methods for node deletion. First is the node like normal BEST, which is if the node is leaf, remove it. If the node has one child, replace it with another child. And if the two children are in here, we will replace it with the according in order successive. And second one is rebalance tree. Rebalance tree is actually quite complex by recalculating height and calculate balance factor and apply rotation if needed. This makes AVL tree deletion slightly and more complex to complex than insertion. And so now without much talk, let's go to talk about our code. So let's talk about this code, which will be shown in here. So this version of the AVL tree focus code only focused on deletion and rotation and rebalancing without including any insertion logic, because we were talking about deletion. And that's it. The tree in here stores with keys left and right child and height. Whenever node is removed, the program checks the tree deletion cases, and which is right rotation, left rotation, and balancing, double rotation. So deleting a leaf node, deleting a node with one child, or deleting a node with two children, which is handled using in order successive. After deletion, the tree may become unbalanced. So the height is updated and the balance factor is calculated. If the tree become left heavy or right heavy, appropriate rotation will be performed according to the functions. And this includes simple left or right rotation, and in case where the child leans the opposite direction, the double rotation is used. The rebalancing method ensures that the AVL tree always maintain a height difference of no more than 1. Finally, the print function shows that in order transfer after the delete, demonstrating that even without insert, the tree can still stay perfectly balanced through rotation. So if we take the output of this code, when we run this simply AVL deletion program, the output we see is the in-order transfer of the AVL tree after performing a deletion. In-order transfer always print the tree in sorted order, which means like in our case 20, 30, 10 to 20, 30, 40, 50, 60, like that. So it's a good way to confirm that the structure is still correct after removing nodes. For example, if we delete the value 10 from the tree, as we've seen in the code, the program balanced and affected the nodes using rotation if necessary, because we have functions like that in our code. And the print is updated sorted sequence of keys. This confirms two things. First is the deletion was successful, and the second, AVL tree maintained its balanced structure using rotations. Even though we remove a node which is 10, the height of the remaining nodes were updated and appropriate rotation was applied in any part of the tree to become left heavy or right heavy. So printed output shows the cleaned up balanced version of tree after the deletion operation. So as we talk, our video has come to end. So before going, let's summarize what we talked. AVL tree are self-balancing binary searching trees with more function actually. They maintain height balancing using rotations, which we call LL, RL, RR, RL, LR. And the demonstration deletion has two steps, which is normal BST, deletion, and then balancing. An AVL tree keep operation efficient at omega, a big omega. So with this, we will end our video and let's meet in the video. Please don't forget to subscribe and comment on this video. Thank you.